Okay, so here is my talk. I'm going to jump right in and talk about some of the accepted impacts, some of the things that we've observed that were documented in the fourth assessment report of the Intergovernmental Panel on Climate Change. I think some of you are familiar with it. I wouldn't be surprised if most of you have not read every page of their large report. So I'm going to give you some selected highlights from it, and then as I go on in the talk, move to more recent results and anticipated and unanticipated impacts. So this is a figure from the fourth assessment report showing sea surface temperatures for the whole globe, and then for the northern hemisphere and the southern hemisphere separately. The red bars indicate annual averages of observations of sea surface temperature from both satellites and in situ measurements, thermometers that we have in the ocean. This is over an extended period from 1850, from the beginning of the Industrial Revolution. One of the things that I want you to see in this figure is this dashed line that indicates what the third assessment report suggested as the interpretation of those results, a smooth curve representing the change in sea surface temperature over that extended period of time. So the dashed line shows the third assessment report. These lines show smoothed analyses by different research groups. And I'm going to remind you of the accepted interpretation, the received wisdom that this climate community has about this record of changes in temperature from 1890 to about 1940. There was a period of steady warming, not extremely fast, falling temperatures in the intervening years, or perhaps steady temperatures, the interpretations vary, and then a renewed period of warming since 1970. The reason I'm showing this figure is to remind you of that accepted interpretation, but also to note that in the fourth assessment report, they looked back at what the third assessment report had shown, and the evidence here suggests that the interpretation, the accepted wisdom by the climate community doesn't overestimate the effects. In fact, if anything, we tend to underestimate the effects. Scientists are by their nature conservative in the sense that they try not to say things that they can't be sure of. They hedge their statements to make them defensible in as strong a way as possible. This is a very different graph showing what appears to be a similar time series, an extended period of time, and the thin lines are observations, the thick lines are simulations by climate. So these are climate model estimates of the global average temperature in two very different sets of model runs. In this, there were dozens of climate models that were used to simulate a whole century of climate. And the model runs were by design set up in two very different ways. One set of simulations, shown in the bottom, is a counterfactual scenario, a scenario that doesn't match what happened in reality. In that set of simulations, the models turned off the emission of greenhouse gases by humans. So we cut back as if everybody was an environmentalist starting in 1900. Those simulations are shown in blue at the bottom here. In the upper panel, we have a simulation in which all of the effects of human-induced climate change were included in the model scenario. And the black observations, the line indicating the observations, is the same in both cases. Look at the counterfactual simulations. When you don't include the anthropogenic greenhouse gases, the models indicate that this warming that we've observed, especially since 1970, wouldn't have occurred. And so the models say we can't account for the warming unless we include the anthropogenic greenhouse gases. Another factor that's shown in this figure are the occurrence of major volcanic eruptions. This reminds us that nature is, of course, extremely variable. Volcanic eruptions cause global cooling by putting gases in the atmosphere which are oxidized to aerosols in the stratosphere. And so you see drops in temperature associated with that. When you include those in a model simulation, the simulation agrees with observations better than if you don't. When you include anthropogenic greenhouse gases in the model simulation, the simulations agree with observations better than if you don't. Okay, so let's talk about some more recent things that have occurred since the IPCC fourth assessment report. The melting of ice, both in ice sheets, that is glaciers, and in sea ice, has been much larger than expected, much larger than predicted. The melting rates have exceeded predicted values, especially in the Arctic. Now, melting sea ice doesn't change sea level, but it has impacts on the environment nevertheless. The ice has a high albedo and reflects sunlight, keeping the environment cool. As soon as the ice melts, the albedo decreases and the heating increases. That can affect both the ocean and adjacent land areas. For example, permafrost that's on the land nearby may be warmed by this. Many scientists are concerned about this because permafrost in general contains huge reservoirs of carbon in the form of peat and also greenhouse gases that are trapped in the ice. When that permafrost melts, there's increased microbial decay of carbon-rich materials in the peat and release of greenhouse gases. This is a big concern. So even though that's a terrestrial effect, it's impacted by the melting of sea ice. For me, a deeper concern, more fundamental concern, is that we didn't predict this. Our ability to predict melting of ice is really not very good. We're just not very good at it yet. So we didn't predict this rapid change, and even though a lot of effort is going into ice modeling, I think our abilities are not as good as they should be. So I'm concerned about that. Now, a lot of press has been, a lot of space in the press has been taken up on this, and I think it's an important concern. The opening of the Arctic, because of the melting of ice there, the potential for having an ice-free Arctic much sooner than expected means we will exploit resources that are there, fisheries, oil and gas under the seafloor. There's going to be environmental impacts from that kind of exploitation. And I think that's a serious concern. The fact that some people are, making extreme statements about this should not lessen our concern. We can set aside extreme statements and say, let's be serious about this and take it as an important impact. Let's talk about changes in tropical storms. There have been apparent changes in the occurrence of the most intense tropical storms. I'm not talking about increased frequency of storm formation, but a higher fraction of the storms that do occur are very intense. And even though this had been discussed in AR4 and the idea had been brought out earlier, there's been increasing evidence of this since the fourth assessment report. The idea is that since there's a larger and larger area of the sea surface that exceeds the threshold for tropical storm formation and growth, that means that there's the potential for more intense storms forming. The impacts on coastal environments are widespread and well known, and that's a factor, and work is going on both on this campus and in other areas to assess and think about ways in which those effects can be reduced or controlled. Now, let's talk about, I want to talk about a scientific aspect that's related to tropical storms, but not to the increased occurrence of high-intensity storms. There's a natural variability in the occurrence, in the distribution of tropical storms. During El Nino years, the number of Atlantic tropical storms is reduced. I could give you an hour lecture about that if you'd like. Just try me. But meanwhile, in the far western Pacific, there's also a reduced frequency of tropical storms in an El Nino year. But at that same time, in the Central Pacific, both in the North Pacific and the South Pacific, and in the typhoon region in the Western Pacific, tropical storm frequency occurs, increases during El Nino years. So there's a natural variability in the distribution and occurrence of tropical storms. So what? Why are we talking about this in a thing that has to do with climate change? We've observed changes in the duration and frequency of occurrence of El Nino events that may be related, perhaps not caused by, but may be related to climate change. And that means that the distribution of tropical storms that we're used to could change. We need to be aware of that possibility. Okay, winds and waves over the ocean. Data both from moored buoys and from satellite observations have indicated significant increases in the average wind speed over the ocean and in the occurrence of large amplitude waves. Surface waves are forced by winds, and stronger winds can mean higher waves, stronger waves. So in some areas there's a causal link. There's a relationship between the stronger winds and the occurrence of higher waves. In other parts of the world, there's not a direct correlation, and we're not yet clear what the relationship is. Now, global warming may or may not contribute to these effects. It does likely impact, it does likely force some of the increase in the surface winds, but that's not the only factor. There are other factors involved as well. So we've anticipated that the global circulation of the atmosphere will change because of global warming. The jet stream lies at is found at the boundary between cold polar air and higher temperature tropical and subtropical air. As the tropics expand, as warming occurs, we expect the jet streams to migrate towards the poles. We've observed that. These surface winds, of course, are at a completely different level than the jet streams winds. So the circulation of the atmosphere is changing, and that has an impact not only on the distribution of where mid-latitude storms fall, but also on surface winds. I'm going to run out of time. Okay, so the ocean has been a sink for carbon dioxide for thousands of years. This is a map of the estimated deposition or downtake of carbon dioxide from the atmosphere into the ocean. The tropical oceans emit carbon dioxide. The subpolar and polar seas take up carbon dioxide. That's been going on for millions of years. In the Atlantic, the formation of deep water means that this carbon dioxide rich water from polar regions is drawn down into the ocean, and that CO2 is then trapped. As the environment changes, the distribution of that flux of carbon dioxide changes. So we estimate that between 30 and 40% of the carbon dioxide that we've emitted into the atmosphere, the excess carbon dioxide we've emitted since the Industrial Revolution began, we estimate that fraction has gone into the ocean. But there's a lot of processes that are changing, and there's the potential for critical changes. That is, it's no longer unusual for scientists to say, as these processes change, we may find ourselves in circumstances where the drawdown ceases or reverses. The meridional overturning circulation, the sinking of cold, salty water in polar regions that pulls that water down to the bottom of the ocean, that takes CO2 down with it. The meridional overturning circulation varies in its intensity over geologic time. We don't see any direct evidence that the meridional overturning circulation has slowed, but that potential does exist, and that's something that we need to look into. The acidification of the ocean means that its ability to take up carbon dioxide from the atmosphere by the physical chemical processes, that changes as the ocean is acidified. And so the capacity of ocean surface waters to take up carbon dioxide is changing. I want to talk briefly about things related to those two factors. Ocean circulation changes are forced by many things, including increased precipitation and melting of sea ice. The polar seas are freshening. In particular, the Arctic, the Atlantic Arctic Ocean is freshening because of the melting of sea ice and runoff from melting glaciers on land. That tends to weaken the formation of the meridional overturning circulation because the water at the surface doesn't as easily find itself in highly saline, very cold conditions. Again, I'm not arguing that the MOC is shutting down, but there will be changes in the circulations caused by these rapid changes in the environment. In the Antarctic, there's a westerly wind. There's a wind from west to east that drives an Antarctic circumpolar current. That current is an important mediator of ocean chemistry. And there have been changes in this circulation, and observations are being made and analyses are being made. But that's an example of a place where there's an important role that the ocean plays, and as the circulation, both of the atmosphere and ocean, changes, we need to accelerate our studies to understand the implications of the changes that are occurring. Okay, very quickly, you're aware that ocean chemistry is changing. The ocean is becoming more acidic because of the uptake of carbon dioxide. There are a lot of organisms that rely on ocean chemistry to build the shells that they live in. And so the business of decreased calcification is a serious concern. I summarize here that crustaceans are not directly affected by this, but mollusks are, and of course you're aware that corals, calcification in corals has been raised as a significant issue. Coral bleaching occurred naturally long before anthropogenic global warming took place, but bleaching has increased in its frequency and intensity, and that's a concern. Bleaching has always been widespread during El Nino events, but again, with increased acidification of the ocean, the bleaching has become a bigger concern, and as the occurrence of El Nino events has shifted with global warming, there's evidence that the extent and duration of bleaching has increased as well. Okay, we're getting towards the end of what I want to say, and these are climate simulations going into the future. So this is again a figure from the fourth assessment report, and it shows the record of global warming up to the average, global average temperature from 1961 to 1990, and then shows projections into the future, making different assumptions about the way in which humans will deal with the environment. Steady as you go change, or a rapid implementation of emissions controls, or I think someone might say this would be the European model, cut down everything, taxed. All of that leading to eventual stabilization of the global warming. Scientists have been aware for a long time that even if we stopped emitting greenhouse gases yesterday, we've already committed to a significant climate change because of carbon that's already in the environment. I've got three pretty pointed remarks. This is in part my opinion. The observed temperature trend has generally exceeded the simulation results. That is, the simulated results are not extreme. Scientists have been conservative in promulgating those results. The emissions of greenhouse gases, where we have tried to control the emissions, we've not succeeded. No matter what mechanism we've used to try and control emissions, I'm not aware of any place in the world where emissions have fallen below the targeted amount. We set a target, we say, well, let's do these things to try and reduce our emissions. And then we tax, we regulate, we do all kinds of things. Somehow the emissions still exceed our targeted amounts. This is not good news. The committed climate change that's shown here, it's wrong. The new estimates show the committed climate change is higher than this. So am I trying to preach doom? No, I'm trying to preach concern. And you can see that there's a lot of factors. And if you want to hear more about what I think about these things, sign up for my course. Okay, so I've listed a couple of references here. These are things that are not in your reference list. These are not particularly profound or comprehensive, but they're sources that I used in some of the words that I spoke today.